In this video, we're going to take a slight break from developing new rules for derivatives. Don't worry, we'll get back to that shortly. But for now, we're going to focus on the process itself and the idea that, when you take the derivative of a function, you essentially get back another function. So the question is, can that derivative be differentiated again, right? So our concept in this video is the process of differentiation under certain circumstances can be repeatedly applied to a given function. And that gives rise to the idea of higher order derivatives, right? So before we look at a few examples, let's just talk a little bit about some of the notation that goes along with it. So you're able to recognize what the notation might be asking you, right? So we have y equals f of x, right? So this is our, what we might call the original function, right? Well, we have notations for the first derivative. So the Leibniz notation is like that, or we have the prime notation that looks like this. So this is the result of applying the derivative operation once. But again, as we've seen, when we derive a function, we get another function. And then maybe this function now is differentiable, right? So if we were to differentiate it again, this is how the Leibniz notation would look. So you would be taking or finding the derivative of dy dx. Now this is a pretty cumbersome notation to have to write down. So there's a way we try to simplify this notation. Now in the numerator we have two d's, right? Two d's. So we can use our exponent notation to kind of combine these two, and then we'll keep the y there. And then in the denominator we have two dx's. So it's like we have dx and then another dx. And even though this is not a product per se, we're going to use again the exponent notation like this, right? And then what would it look like if we use the prime notation? Well, that's easier. If one prime represents one derivative, then if I want to differentiate twice, then I'm going to use two primes, and then we put of x, right? And now the fact that we have, again, a given function, we've differentiated once and got this, differentiated now twice and got this, it means it makes sense that we can start referring to this as the first derivative, right? So that's what we would refer to this function here as the first derivative of f of x, right? So this is the first derivative of f of x. Well, then this would be the second derivative. I'll just go ahead and abbreviate the second. So this would be the second derivative of f of x. And again, differentiation is so much fun. Let's do it a third time. So what does it look like? Well, now in the d notation, we have to take the derivative of this function. So now it's the derivative of the second derivative. And again, so we already have two d's here in the second derivative, and now we have a third d here in the top of this fraction, even though it's not truly a fraction. So it's d cubed y, or d3y, and then in the bottom, again, we have three dx's, so dx cubed. And then for primes, as you might expect, we just put another prime there and end up having now three primes, and that represents the third derivative of f of x, right? Now, after a while, so I think you can see the pattern, and you can see how this notation just evolves after each successive derivative. Now with the primes, if I keep adding a lot of primes, after a while it's just, it's not even gonna probably fit on the page, right? So after about the third or fourth derivative, you'll see this. So let me now write down what the fourth derivative is. So that's when I would take the derivative of the third derivative. All right, looks like that. And then that would mean now d4y and then dx to the fourth. Now, again, we stop writing the individual primes after 3 or 4 derivatives. And what we switch to is we put the actual number of times we're going to differentiate, but it's put in parentheses because we don't want this 4 to be confused with like f raised to the fourth power, right? So what we do is we put parentheses here. That indicates that it's not a power, but instead it's a derivative. And then this would now be the fourth derivative of f of x, right? So let's make it more general now. So this process, again, as long as each function is differentiable and as long as whatever rules apply, right, we can continue this process. And then I'll just say dot dot dot, and then what will happen is you'll go to, I'll just write down what we call the nth derivative. And using the Leibniz notation, it looks like this. Using not really the prime, but the f notation, you'd put an n in parentheses of x, right? And then this is the nth derivative of f of x, right? So higher order derivatives is just a fancy way of saying just keep on differentiating. Now you might wonder, what's the use of all of these derivatives? At least we have one specific use for the first derivative. That's what we use to find the slope of the tangent line. But what about the second? What about the third? Well, depending on your area of study, sometimes you might end up using, the nth derivative or the derivative that you keep getting by differentiating and never stopping. So differentiation now becomes an infinite process. And there are lots of theoretical things that depend on the ability of differentiating a function as many times as possible. But it's not just the theory. It actually has applications in things like signal processing, for instance, in the EE world, right? So again, it's not just because we like differentiation. I mean, that might be just like the cherry on top, but they have practical uses, and we will see for sure where at least the first 3 derivatives will be useful to us, right? Just another quick term that we need to introduce, and then we'll do some examples. So the number of times, and in this notation it would be n. In fact, in both notations it would be n. So the number of times n that a function is differentiated, so that a function is differentiated right? That number is called the order of the derivative, right? So is called the order of the derivative. So like for a second derivative, that would be like a second order. For the fourth derivative, that would be a fourth order. All right. So let's take a look at a few really simple examples. And let's start with, it's always nice to explore whenever you get a new concept or a new process. you always try to see, well, what does it look like for polynomials? It's like polynomials are always the guinea pig, right? So we have y equals, let's say we have a fourth degree polynomial. So something like 3x to the fourth minus 8x cubed plus 10x squared minus 9x plus 15, right? So let's differentiate this function as many times until we get bored. Well, I'll probably never get bored of that, but let's see anyway, right? So the first derivative looks like this. So again, applying all our basic power, sum difference, constant multiple rules, we will get 12x cubed minus 24x squared plus 20x and then minus 9, right? But again, look at what happens. We have another polynomial. The degree went down from 4 to 3, and that makes sense because of what the power rule does, right? Because the power rule is going to reduce all the powers by 1, right? Well, let's write down what the second derivative would be. So we have d2y dx squared, differentiating again using the same set of rules that we did to get the first derivative. Here's our second derivative, 36x squared minus 48x plus 20, right? And again, look, we got another polynomial. Again, this degree is 1 less than this degree. So you probably see what's going to happen after a while. But let's keep going. So the third derivative, right? So our second derivative is a quadratic. Look what happens when we differentiate a quadratic. We're going to get 72x minus 48. So we get a linear function. If we differentiate a fourth time, told you I wouldn't get bored. If we differentiate a fourth time, well, now we're just left with 72. And then I'll write this one in the same line. If we differentiate a fifth time, we will get 0. And then after that, if we were to continue differentiating, we would keep getting 0, 0, 0. So if we start with a fourth degree polynomial, at and after the fifth derivative, they're all 0, right? So you start with a fourth degree polynomial, the fifth and any other higher order derivative is going to be equal to 0. Okay, so let's try another one. Let's do one that requires one of our like either product or quotient rules. So let's take a look at this. So let's say, and this one, so we have x squared, and let's say we have times e to the x, right? And what we're going to find is we're going to find the second derivative of this. So we're not going to go quite as far as we did with the polynomial, but I want to do this at least twice so that we see, again, the repeated use of several rules of differentiation, right? So first derivative, we need the product rule. So again, I will write down what the product rule says that we're supposed to do. We need to take the derivative of the first, so the derivative of x squared times e to the x plus the first times the derivative of e to the x. So e to the x. All right, let me fix that so my e looks better. All right. And then, so now let's actually simplify this. We can't leave it here until we have all the derivatives simplified on the right-hand side. So my first derivative is, so when I differentiate x squared, I'll get 2x, and then that's times e to the x. And then bring down the x squared, And when I take the derivative of e to the x, we know what that is. We have e to the x, right? So that's our first derivative, not too bad, but we had to use our product rule because now we're differentiating the product of two functions, and there's no way to simplify this, right? There's nothing we can do to somehow get rid of that product. Now, if we have to find the second derivative, let's, in this current form, look at what it looks like, what it entails. So we have one product here, the 2x times e to the x, and then we have another product here, the x squared times e to the x. Now, I could do two separate product rules, so one for the first product and one for the second product, but because both terms have an e to the x in common, I can use the greatest common factor and I can factor out that e to the x. In other words, if you notice here, we started with a quadratic, like an x squared times e to the x. If I were to factor out an e to the x, and let's say I put it on the right hand side, just like it is in the original function, in parentheses, I would have 2x plus x squared. So I would have another quadratic here times my e to the x. So let's see what happens now when I apply the product rule again to this function, right, to find the second derivative. So d2y dx squared, that's equal to, so again, let's write down what the product rule says. Take the derivative of the first, so that's 2x plus x squared, times the second, plus the first, and since it's a quantity, I'm going to use my parentheses, and then times the derivative of the second. All right. Now let's write down the simplified derivatives and see. And then, this pattern makes me wonder, when we find the second derivative, can we still write it in the form where we have a quadratic times e to the x? Well, that's one way to find out. So when I take the derivative of 2x plus x squared, I will have the quantity 2 plus 2x, and that times e to the x, and then plus the quantity 2x plus x squared, and the derivative of e to the x, again, is e to the x. So look, we have the same pattern. Because of that nice property of e to the x, that e to the x is its own derivative. That's why we keep getting factors of e to the x in both terms. So then it does mean that I can write my second derivative in the same form, where I have a quadratic times the exponential function. So let's write that down and then end this particular example. So again, if I factor out an e to the x and put it on the right, well, I have a 2 plus 2x left here, and then I have a plus 2x plus x squared left from the second product here. So I have plus 2x plus x squared, and now I actually have a pair of like terms in the parentheses. So this simplifies to 2 plus 4x plus x squared times e to the x. And it does follow that pattern. Yes, the quadratic seems to be gathering, like it's getting more and more terms. Like this one just had a single term, this one had 2, this one had 3. Now a quadratic in simplified form or standard form can't have more than 3 terms, right? So we would expect it to stay the same for the third derivative. But why don't you try it? Why don't you try it? Differentiate this a third time and see if you can follow this particular process and if we can still get it as a quadratic times e to the x, right? Kind of an interesting example there. Hopefully you explore and try a few more derivatives and see what happens. Okay, so here's our last example. I'm going to take a really simple function. Let's just take like a reciprocal function, but instead of 1 over x, let's do something bold. Let's go for 2 over x, right? And let's find like the fourth derivative of this one. And for this, I'm going to use the prime notation. And I look at this and you might say, okay, am I going to have to do the quotient rule every single time because of this quotient? Technically you could, right? Even though, and you know, there's a constant function in the numerator, you technically could do your quotient rule, but I think that would be overkill. The reason is, I can use using my properties of exponents, I can write 2 over x as 2 times x to the negative 1. And this way, all I need is the power rule. I just need to, well, technically power and my constant multiple, but I'll keep this constant here and then apply my power rule to the x to the negative 1, and that will give us our first derivative. And this is what it would look like using the prime notation. So then bring down the negative 1, multiply the 2, so we'll have negative 2 times x, and then subtract 1 from this, and this becomes negative 2. Right? Now, if we were stopping at the first derivative, and let's say we wanted to write our final answer without negative exponents, then we can use the same property that we used here and rewrite that term. But since we're going to continue the differentiation process, I'm going to leave it with that negative exponent, and that way the power rule will continue to apply. So again, I can use my power rule over and over. So here is the second derivative, right? So negative 2, bring down the other negative 2, that makes a positive 4, and then subtract 1 from the exponent. Right? Now, again, if we think back when we did the polynomial, we notice each time, you know, the power got lower and lower until all the terms, after repeated differentiation, all the terms ended up being equal to 0. Well, that's not going to happen here. Well, first of all, this is not considered a polynomial because you have a negative exponent. But when I see, because my exponent is already negative, once I keep subtracting 1, it's just going to become more and more negative. It will never get to 0. We're already past 0 because we started with an exponent of negative 1, and when we keep subtracting, again, that exponent is just going to become more and more negative. So the third derivative, and what I will do, I will switch over to that alternative notation, but then put the 3 in parentheses to indicate that it's differentiation that we're doing. And then bring down the negative 3, so that's negative 12, and then we have x to the negative 4. And this is one that, again, could go on and on and on, but the difference with this, as opposed to the polynomial example that we saw earlier, these terms will never get to 0. Never, right? So let's write down our fourth derivative as promised, and then that becomes a positive 48 x to the negative 5th. Now, if we know that this is where we're going to end, and if we want to write our fourth derivative so that it looks like, or at least in the same format of our original function, then this becomes 48 over x to the 5th. Right? So again, another interesting example of repeated differentiation, and I encourage you, take a couple functions. It doesn't have to be overly complicated. Differentiate them a couple times and see if you see, interesting patterns like this, or patterns like with the polynomial, that after a while everything just becomes 0, right? So, the moral of the story of this video is if I can differentiate once, and I can, then I can differentiate twice and have some fun while doing it. Right? See you in the next video.